Hi, this video is going to cover section 6.1, discrete random variables. So the first objective that we want to do is to distinguish between discrete and continuous random variables, right? So we've talked about discrete and continuous variables before, so some of this is a little review. So a random variable is a numerical measure of the outcome of a probability experiment, so its value is determined by chance, right? Random variables are typically denoted using capital letters such as capital X, right? And just another note here about notation is that we use lowercase letters to list possible values of the random variable or the sample space of the experiment. Right? So then there are two types of random variables, discrete and continuous. So a discrete random variable has either a finite or a countable number of values. The values of a discrete random variable can be plotted on a number line with space between each point, right? So for example, if I have a number line, right, and I'll just label this 0, 1, 2, 3, 4, 5, right, then if your possible values that can take on, right, would be something like points at the spots, right, where the blue dots are, that would be considered discrete, right? There's space in between, right? And you're essentially like counting something, right? So typically with discrete, you're counting, where with continuous, typically a way to think of it is you're measuring, right? And I used this analogy before. I like to think of discrete as like going upstairs, right? Where continuous, you're like going up a ramp, right? So the idea is with discrete, you have to like fit in these like buckets, right, if you will. So you can't be in between two values, where continuous you can be, right? So like when you go up a ramp, you can kind of start and stop wherever, but if you're on stairs, right, you have to be on one step or go up to the next step, right? That's kind of the idea. So an example of a discrete random variable is the number of A's earned in a section of statistics with 15 students enrolled. Right? So if I let capital X be my random variable, and that be equal to the number of A's, right, then little x could take on values 0, 1, 2, 3, 4, so forth, all the way up to 15. Right? It's possible that 0 students would get A's all the way up to 15 because there's 15 students in the class. Right? So then a continuous random variable, right, has infinitely many values, right? So it covers like an interval, right, of different values. So to compare that with the number line above, right, so if I draw a number line with the same values, 0, 1, 2, 3, 4, 5, then a continuous variable would be an interval, so maybe like all values in between 0 and 5, including 0 and 5. Right, so I could pick any values in between those. That would be continuous, right? That covers an interval. So the values of a continuous random variable can be plotted on a line in an uninterrupted fashion, right? There's no interruption. It's just drawing like an interval, right? So an example would be the speed of the next car that passes a state trooper. Right? So if capital S is equal to the speed, then little s could be any value bigger than 0. Right? So that covers an interval span. Right? You could go 60 mile an hour, 61.2 miles an hour, right? There's no the values don't have to fit into a specific bucket, right? We're not counting, we're measuring speed. Right, so then this next example that I have is some practice with determining whether the random variable is discrete or continuous, and in each case we want to state the possible values of the random variable. So like part A for number 1, it says the time it takes for a light bulb to burn out, right? So in this case, time is going to be a continuous random variable. It's like it's a measurement of something, right? So this is continuous. So if t was my variable, the possible values that could take on would be something bigger than 0, right? Part B is the weight of a T-bone steak, right? So if we use the variable w for weight, this would also be able to take on values bigger than 0. This would be continuous, right? I don't have just 13-pound steak. There could be 13.2 pounds and so forth, right? It covers an interval of things, right? Same with the time, right? We're not counting. Part C is the number of free throw attempts before the first shot is made, right? So the idea is you keep shooting until you make your first one, right? And you write down that number, right? If it took you 5 shots before you made your first one. So that implies that we're counting, right? So this would be discrete. So your values that this could take on, if we use just x, that would be 1, 2, 3, 4, and so forth, right? I'm drawing 3 dots there, meaning that there's not an ending point, right? So it's important to understand that just because there's not a clear ending point doesn't mean that it's continuous variable, right? Discrete variables can go on forever, right? So the idea is here, there's not a good number for me to end in, right? Maybe the number 10 would seem reasonable to list, right? So someone's, if someone has 10 shots, they're going to make at least one free throw, right? But it's possible someone would, maybe take 15 shots before they can make a free throw, or maybe someone takes 40 shots, right? So the idea here is there's not a clear good number to pick here, because any number I pick, someone might take longer than that, right? So that's why we don't write an ending value here, right? But notice it's still discrete, right? And that's okay. Right? So then part D says in a random sample of 20 people, the number with type A blood, right? So again, here we're counting, so this would be discrete. and the possible values that it could take on would be 0, 1, 2, and so forth, all the way to 20. Right? If I have 20 people, it's possible 0 of them have type A blood, 1, 2, all the way up to everyone in the random sample has type A blood. Right? So I have a couple more examples of practice. Part E is the number of defects in a roll of carpet. Right? So this would be discrete. We're counting. And the possible values that this variable could take on would be 0, 1, 2, 3, ... Right? Because there's not a clear ending point again for how many defects are on the roll of carpet. Part F is the distance a baseball travels in the air after being hit. Right? So this would be an example of a continuous random variable, and the possible values it could take on would be d greater than 0, right, if d was your variable. Right? So, after you hit it, it's going to go at least 0 feet or inches or whatever unit you're using for your measurement, right? But it could go, it could end up traveling many different values, like 1, 1.3, right? It covers a span, an interval of values. And you're not counting, right? It's a measurement. So then part G says the number of points scored during a basketball game, right? So this would also be counting, so this would be discrete. And the possible values that you could take on when scoring in a basketball game would be 0, 1, 2, 3, ... Right? Because in basketball, you can go up by 1 point, 2 points, or 3 points, depending on the situation. So it's possible to, span all those values. It's also possible to score 0 points in a game, right? And I put ... because there's no clear ending point. You might think like no one's going to score 100 points in a game, and then maybe someone does, right? So then part H is the square footage of a house, right? So when you're taking the square footage of a house, you're measuring. It's a measurement. So this would also be continuous, right? And if you're using A for area, your area of your house could be, anything bigger than 0, right? You couldn't have an area of 0 because then you wouldn't have a house, but the idea is you could have anything above 0, right? All right, so hopefully that review helps you recall the difference between discrete and continuous variables. So objective 2 is helping us be able to identify discrete probability distributions, right? So the probability distribution of a discrete random variable, capital X, provides the possible values of the random variables and their corresponding probabilities. A probability distribution can be in the form of a table, a graph, or a mathematical formula, right? So 3 different ways we can show that. So then example 2, we have suppose that we ask a basketball player to shoot 3 free throws. Let the random variable capital X represent the number of shots made. What are the possibilities of little x, right? So little x could take on the values 0, 1, 2, or 3. Right? So it's possible to make 0 of the shots, 1 shot, 2 shots, or all 3, right? So then right below it says consider this probability distribution for the random variable x, right? So this is an example of a probability distribution, right? I have a table where I see each of the possible values of x and its probability, right? And remember some conditions with a probability distribution that we've already looked at is that the sum of the probabilities have to be 1 and all the probabilities have to be between 0 and 1, right? We'll actually look at that on the top of the next page, right? So I have here a question. It says, how do we denote and read these values, right? So if you see P of x this is read as the probability that the random variable, capital X, equals little x, right? Or in other words, if I pick on this last row, if I have p of 3, or sometimes we might do p with a little x equals 3 inside, right? That's equal to 0.51, and this can be read as the probability that the random variable, capital X, equals 3 is 0.51. Right, so as I stated, the top of this next page is looking and reminding us about the rules for a probability distribution, right? So this still applies if we have a discrete probability distribution, right? So the first condition is that if we add up all the individual probabilities, that has to sum 1, and then also all of our probabilities have to be in between 0 and 1 inclusive, right? So example 3, we're trying to determine whether the distribution is a discrete probability distribution. If not, state why, right? So in part A, we have to check each of these. So the first thing, we need to make sure that the sum is 1, right? So if you add these up, we do in fact get 1, right? So that's fine, right? So in other words, the sum of the probabilities is equal to 0.2 plus 0.2 plus 0.2 plus 0.2 plus 0.2, which is equal to 1, right? So that meets that condition. And then we need each of these to be in between 0 and 1, right? Well, they're actually, in this case, they're all equal to 0.2. So 0.2 is in fact in between 0 and 1. So we're good. We meet that condition as well, right? So we have condition 1 and condition 2 met. So this would be a yes, right? It's a probability distribution. Part B, what should stick out to you is this guy, right? This very last one, that has a probability value that's negative, right? So that is not in between 0 and 1, right? So therefore it's a no. It's not a probability distribution. So we'll just say no over here, right? So that that's not allowed, right? So in other words, the probability of 50 is equal to negative 0.15, which is less than 0, right? Right. So then part C, over a quick glance, all of the probabilities are in between 0 and 1, right? So P of X is in between 0 and 1 for all values of X, right? So we meet that condition. And then if I sum up all of these individual probabilities, right, that actually gets me to 0.95, right, which is not equal to 1, so this would be a no, right? So that both conditions must hold, right, in order for it to be a probability distribution. So then in example 4, we're trying to determine the required value of the missing probability to make the distribution a discrete probability distribution, right? So the three values I have are all in between 0 and 1, and this guy is missing, right? So maybe we let that be equal to t, right? So in other words, we're going to let the probability that x equals 4 equal to t, right? So we're going to want t to be in between 0 and 1, and we're also going to want the sum of these probabilities to be equal to 1, right? So in order to make that happen, I need to let 0.4 plus t plus 0.1 plus 0.2 be equal to 1, right? Because I want the sum of all these to be equal to 1. So I just need to solve for t. So 0.4 plus 0.1 plus 0.2 gives me 0.7. So I get 0.7 plus t equals 1. If I subtract 0.7 from both sides, I get t equals 0.3. And that value, 0.3, is in between 0 and 1, so we're good there, right? So that's going to be my missing value, right? So the probability that x equals 4 is equal to t, which we want to set equal to 0.3. So there's my missing value. Right. So now with example 5, we want to graph the discrete probability distribution from example 2, right? So I'll show you how we can graph a discrete probability distribution. Right, so what we're trying to graph is this table here, right? From example 2. So that's on page 2 of your notes. Right, so to make this graph, you're just going to draw in your x and y axis, right? And then I'm going to label this. This is going to be my number of successful free throws. Right, and then over here we would have p of x. Right, that's my probabilities. So then my discrete values I could take on, we could take on 1, 2, 3, and also 0 was possible, right? But that would be right on the x-axis. And then the probabilities, I'll go up by 0.1 each time. Right. So looking at that table, so what we're going to do when we graph this, you're just going to have like a dot with like a line going down to the x-axis, if you will, right? So like the first one, an x value of 0, that goes up to 0.01, which would be really tiny, right? So just draw a dot and draw a line up to that dot, right? For 1, that goes up to 0.1, so I'll draw a dot here and then draw a line down. And then for 2, that's 0.38, right? So we draw a dot about at 0.38 and then draw a line down. And then for an x value of 3, the probability is 0.51. So draw a dot about 0.51 and draw it down, right? So that would be a graph of this probability distribution, right? So you kind of have like these skinny bars, if you will, going up to those values. So it's not quite like a histogram, but sort of like that in a sense. But notice, this is discrete, so there's no values in between, right? There's nothing in between 2 and 3. That's why I have a line just at the number 2. Right? And so we're also asked to discuss what's the distribution shape, right? So this looks, something like this, where we have a long tail on the left. So this looks to be left skew. Right. Right, so objective 4, what we want to do is compute and interpret the mean of a discrete random variable. So in example 6, the example I have, it says one semester I asked a small statistics class of 10 students to disclose the number of people living in their households. I obtained the following data. So I have that data set. Part A, what we're asked to do is to create a table to show the probability distribution, right? So in order to make, our goal is to have a table that shows all the possible values for x and the probability of that happening, right? So the different values for x, if you look in this data set, x could be 2, 3, 4, 5, or 6, right? So what we need to do is be able to fill this in, right? So to get there, what I would recommend is we need to create a frequency distribution and then a relative frequency distribution, and that's going to be our probability, right? So in other words, I need to fill in this table. Oops. So that way I can figure out the probability. Right? So if you count in this data set, there are 2 2s, 1 3, 3 4s, 2 5s, and 2 6s, right? So we just need to look in here and count how many of each of the items that we have. If we add these up, there are 10 total items. So then the relative frequency would be its frequency divided by 10, right? The total. So this would be 2 over 10, which is 0.2, 1 over 10, which is 0.1, 3 over 10, 0.3, 2 out of 10, which is 0.2, and 2 out of 10 here again, which is 0.2. So then these values are just going to be the probabilities, right? So we'd fill these in. And that's my frequency distribution, right? So that's part A. In part B, we're asked to compute the mean number of people living in the 10 households, right? So the mean is equal to the sum of all the x values, right, divided by how many we have, capital N. So this would be equal to, so now I'm just going to list my data numbers, right? So I have 2 plus 4 plus 6 plus 6 plus 4 plus 4 plus 2 plus 3 plus 5 plus 5. This would be all over 10, right? Because there were 10 households. So from here, we could simply just add up the numerator and then divide by 10 to get the mean. But I'm actually going to work this through a different way, and the rationale is so that way we can kind of see how we can arrive at this formula at the bottom for how to calculate the mean of a discrete random variable, right? And this equation at the bottom is going to be easier for us to use, right? And it's going to come in handy. So the first thing that I want to do is rearrange the numbers in the top and group like numbers together, right? So group the 2s, the 3s, and the 4s, and the 5s, and the 6s together, side by side. And I can do this because of the commutative property of addition, right? The order that we add things in, we can change that, and it doesn't affect the sum, right? So I have 2 plus 2, and plus, and then there's just 1, 3, and then we have 3 4s, and then 2 5s, and then 2 6s. Right, and this is all out of 10. Right. Next, what I want to do is, instead of writing 2 plus 2, I can use multiplication to show the repeated factors, right? So for the 2's, there's 2 of them, so I can show that as 2 times 2. For the 3, there's just 1, so 3 times 1, plus 4 times 3, because there's 3 of those, and then plus 5 times 2, there's 2 5s, and then 6 times 2, because there's 2 6s, right? And then now what I can do is use properties of fractions to split this up to be 2 times 2 over 10 plus 3 times 1 over 10 plus 4 times 3 over 10 plus 5 times 2 over 10 plus 6 times 2 over 10. Right, so we're splitting it up into separate fractions. So essentially I'm like adding the fractions but in reverse, right? So if I give you this, you would add to get that, right? And when you have the same denominator, you can add their numerators. So I'm kind of doing that in reverse. And then now what we can do is pull this first factor in the top, pull it out in front, right? So it's kind of like multiplying fractions but in reverse. So the 2 times 2 over 10 can be written as 2 times 2 tenths plus 3 times 1 tenth plus 4 times 3 tenths plus 5 times 2 tenths plus 6 times 2 tenths. Right? So then with the probability distribution that we just had gotten, you should notice that this number that's a fraction, the second factor in each of these, is the probability of the number that's being multiplied by the probability of that happening, right? So in other words, this is the same thing as 2 times the probability of 2 plus 3 times the probability of 3 plus 4 times the probability of 4 plus 5 times the probability of 5 plus 6 times the probability of 6. Right? So that's just equal to 2 times 0.2 plus 3 times 0.1 plus 4 times 0.3 plus 5 times 0.2 plus 6 times 0.2, right? And if you multiply those together, we get 4.1, right? So I know that's a long about way to get that mean, but again, we are just exploring where that equation comes from, right? So to find the mean of a discrete random variable, what you can do is take the x value and multiply it by its probability and add all those up, and that will give you the mean. Right? So for example, in example 7, we're asked to compute the mean of a discrete random probability distribution, and this is the example. This is from example 2. So there's 2 ways that we could go about this. The first way to compute the mean, we could use the equation. Right here. So this is just a fancy way of saying take each of the individual x's times its p of x and add those up, right? Because remember, the capital sigma means to add, right? The sum. So this would be, 0 times 0.01 plus 1 times 0.10 plus 2 times 0.38 plus 3 times 0.51, right? So we're multiplying each of these, right? So then if I multiply those and add those together, you should get 2.39. Right, so that would be my mean. So that's one way to do it, using that equation. Another way is if you want to kind of do like a table format, we can add another column, which is x times p of x, and I can multiply these values together and write down their product here, right? So 0 times 0.01 is 0, 1 times 0.1 is 0.1, 2 times 0.38 is 0.76, and 3 times 0.51 is 1.53, right? And the sigma means the sum, so if I add this column together, I get 2.39, and that is equal to the mean of x. Right? So then we want to interpret this mean. So the interpretation of this mean in context to the problem, it would be the following. If we repeated the experiment of shooting free throws many times, we would expect the number of free throws made to be around 2.39. Right? So that would be interpretation of that mean, right? So if we did the experiment a whole bunch of times, that's what we would expect to happen, right? So because the mean of a random variable represents what we would expect to happen in the long run, it's also called the expected value, right? And we denote it with the following, right? So we have a capital E, and then in parentheses you put the random variable, right? So capital X. So then in concept 5, we want to be able to interpret the mean of a discrete random variable as an expected value, right? So example 8, it says the graph of the discrete probability distribution represents the number of rooms in a rented housing unit in 2017, right? So we have this distribution, right, given as a graph. And then we have some questions about this. So part A says, what's the probability that a randomly selected rental unit has 5 rooms, right? So that would be the 0.198, right? Looking at what I just circled. So the probability that x is equal to 5 is equal to 0.198. Part B says, what's the probability that a randomly selected rental unit has 5 or 6 rooms, right? So the probability that x equals 5 or x equals 6, right? This would be equal to, using the addition rule, would be the probability that x equals 5 plus the probability that x equals 6, right? We can add those together. So if we pull that from the graph, right, we're adding these two together, right? So this would be equal to 0.198 plus 0.103, which that sum is 0.301. So then part C says, what's the probability that a randomly selected rental unit has 7 or more rooms, right? So we're trying to figure out what's the probability that x is greater than or equal to 7, right? So looking at this, we can only have 7, 8, or 9, right? So this would be equal to the probability that x equals 7 plus the probability that x equals 8 plus the probability that x equals 9, right? There's no option for bigger than 9. So if we add up those individual probabilities, this would be 0.039 plus 0.018 plus 0.008, right? Add those together and we get 0.065. Right? So that's the probability that x would be greater than or equal to 7. So now, part D, it says if a rental unit is randomly selected, how many rooms would you expect the unit to have? Right? So remember, the expected value of random variable is equal to the mean of the random variable, right? And we already found that this is equal to the sum of all the individual probabilities times the x value, right? So this would be equal to 1 times 0.009 plus, so we have to multiply those together, right? So 1 times 0.009, 2 times 0.017, right, and so forth, all the way down. All right, so I'll write these down. Right? So that sum is equal to 4.355, which is approximately 4.4. So we would expect a rental unit to have 4.4 rooms on average, right? So we would expect a rental unit right? And obviously we can't have 4.4 rooms, so we would expect like 4 to 5 roughly would be the expected value of the average, right? The mean number of rooms, which is also consistent if we look at the picture, right? The distribution, because notice the mean, it seems likely, seems logical that it would happen, somewhere around here, right? In the center. Right, so this looks to be, fairly symmetrical, right? All right. So the next example, example 9, is an example using life insurance. So this, this example is pretty involved. It uses a lot of things that we've talked about probability. So example 9, it says a term life insurance policy will pay a beneficiary a certain sum of money upon the death of the policyholder. These policies have premiums that must be paid annually. Suppose an 18-year-old male buys a $250,000 one-year term life insurance policy for $350. According to the National Vital Statistics Report, Volume 58, Number 21, the probability that the male will survive the year is 0.998937. And we want to compute the expected value of this policy to the insurance company and interpret this result, right? So something to keep in mind is throughout this whole example, we're through the lens of the insurance company, right? So, the goal, because we know that the expected value, right, of a random variable is equal to the mean of the random variable, which is equal to the sum of the individual probabilities times the x values, right? This is what we're trying to find. That's our goal. What's missing is we don't have a table that shows this, right? We need to come up with this probability distribution table, right? We need this. So we're going to have to think through what this is going to look like, right? So first thing to note is that there are two possible outcomes. right? One possibility is the person lives or survives the year. The second possibility, and I'll just put survives. The second possibility is that the person dies. There's death, right? So I'm going to put that in the table. There's just going to be two possibilities. So we have survives and we have death, right? But what we need to put in the x value, right, we need to have some kind of quantity to put there to show the situation, right? So if we let capital X be a random variable that represents the payout. This could be money lost or gained, depending on the survival or death of the assured. Right? So that's what my capital X value represents, that variable, right? Something else that we need to realize is that the complement of someone surviving would be death, right? That they die. So in other words, using the idea that there's only two options, the probability of surviving plus the probability of dying is going to equal 1, right? But something we know from the reading, right here, is that the probability of surviving is equal to 0.998937. Right? So that means, by the complement rule, that the probability of dying is equal to 1 minus the probability of surviving, which is equal to 1 minus 0.998937, which equals 0.001063. Right? So basically, so far, what we figured out is what these P of X values are, right? So surviving, that probability is 0.998937. Right? And then the probability of dying we found to be 0.001063. So now what we need to be able to fill in these possible values for x, right? So we need to think through this a little bit. So if capital X is the payout, right, depending on the death of the insured, we need to think about what happens monetarily to the company, right? So if someone survives, right, so let's look at it in the two possibilities. If the person survives, the company, or survives the year, the company pockets $350, right? And they don't pay out anything. So the net gain is $350, right? But if the company dies, right, or not the company, but if the insurer dies, right, the company gets $350 still. But then we have to pay out $250,000, right? Because that's the policy amount. So if you take 350 minus 250,000, that gives you negative 249,650. Right? That's how much money the company loses for that year, right? For that person if they end up dying. So now we can fill in these amounts, right? So this would be, we would put 350 here, and negative 249, 650 would go here. So now we have what we needed, that probability distribution table, right? So we had to think through to be able to get that. So the expected value of x is equal to the mean of x, which is equal to the sum of the x's times the p of x's. Right? So this would be equal to 350 times 0.998937 plus negative 249, 650 times 0.001063. Right? So if you simplify that, you should get positive 8425. Right? So that is the expected value. Right? So in other words, the company is going to expect to make 8425 for each 18-year-old male client it insures. Right? The 8425 profit of the insurance company is a long-term result. It does not make $84.25 on each 18-year-old it insures, but rather the average profit per 18-year-old male insured is $84.25. So because this is a long-term result, the insurance idea will not work with only a few insured. Right? So the idea here is that we need a lot of people insured. If we have a lot of people in this category, that's how much we're going to make on average. Right, but again, we don't make $84.25 per person. Right, that's not how that will work. Right, and you can imagine if you're a company, we're going to want that expected value to be positive. Right, so that way we're not losing money. All right, so the last learning objective in this section is computing the standard deviation of a discrete random variable. So the standard deviation of a discrete random variable is given by the following two formulas, right? So we can use the first one or the second formula, right? So personally, I think using this second formula is a little easier to work with. So we still have little x as the value of the random variable, mu sub capital X is the mean of the random variable, and p of little x is the probability of observing a value in the random variable. Right? So in this example, we have multiple parts. It says Powerball is a multi-state lottery. The following probability distribution represents the cash prizes of the Powerball with their corresponding probabilities. Right? So I looked up the Powerball. I think it's something like 45 states participate in the Powerball, right? So it's pretty big multi-state lottery. So we have the probability distribution here where it lists the different cash prizes and then the probability for each of the prize occurring, right? And notice it says just grand prize because the grand prize is something that changes in a lottery like this, right? So you may, if you pay attention, someone might talk about like, oh, the Powerball is up to 20 million or whatever it might be up to. So that's the idea of why it just lists grand prize. But these prizes would stay the same, right? Just the grand prize is fluctuating, right? So we have the probability distribution. So in part A, it says if the grand prize is $15 million, find and interpret the expected cash prize. If a ticket costs $1, what is your expected profit from one ticket, right? So this grand prize, we're filling in amount of $15 million, right? So to find the expected value, I'm going to have to find the mean, right? So the expected value here would be equal to the mean of x, which is equal to the sum of the x values times its probabilities, which would be equal to 15 million times its probability, oops, 684. Right, and then we'd have, plus 200,000 times its probability. So there's what, 1, 2, 3, 4, 5, 6 zeros there, I think. And then 28. Oops, it's not. Let me write there. Right, and then plus, and then fill the rest of those in, and the last one would be 0 times 0.972, so forth. Right, so I'm not gonna write all that out, because I'm actually gonna type this into my calculator, so that way it'll actually be easier to get some of these other values. Right, so you can write all that out if you'd like. But I'm going to pull up calculator. Right. So these probabilities are pretty messy, right? They're a lot of digits long. Some of them are really small, but this is a real world example, right? Sometimes they're really messy. So what I want to type in here is the calculate the mean, right? So I would type in 15 million. Right, make sure 1, 2, 3. Yep, I got that. And then I'm multiplying that times 0 point, and then make sure pretty sure there's 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. And then 684. Right, so that's a really small probability, right? And then we'd have plus 200,000 times, and then its probability, we got 1, 2, 3, 4, 5, 6 zeros. 1, 2, 3, 4, 5, 6, and then 2, 8. And then plus 10,000 times 0 point. And then there's, let's see, 1, 2, 3, 4, 5 zeros. 1, 7, 1, 1. And then plus 100 times, and this one has just 3 zeros, so 0.123 zeros, and then 153, 996. and then plus, then we have 7 times 0.004 778,961, and then plus 4 times 0.007881463, right, and then plus 3 times 0.01 45450 116, and then plus 0 times 0.97 268 24, and then 3 2s. Shoo, right? So that's a lot to type in, right? So again, the reason why I wanted to plug this in my calculator is I'm going to want to try to avoid plugging in a bunch of these numbers, and we're going to need some of these values later on as well, right? So if I hit equals, I get the mean, right? That's my expected value, right? So let me go back to the note page and we can write that down. Right, so this comes out to be equal to 0.299591659. Right, those are all the digits on my calculator, which is approximately 0.30, right, if we like round to the nearest cent, right, so hundredth spot. So what this means is the expected cash prize is 30 cents. Right, so on one ticket we can expect to make 30 cents, right? But we're paying $1 for that ticket, right? So after paying $1, right, you would expect, so your expected profit is going to equal -1 plus 0.30. Right, so that's what you pay, and that's your payout, right, your expected payout. So that gives me 70 cents. Right, so in other words, we're expecting to have a net profit of negative 70 cents. Right, we're losing 70 cents. Right, so then the next part here, part B, says if the grand prize is $15 million, the nearest dollar, what is the standard deviation of the cash prize, and what does this value suggest, right? So the square root, or excuse me, not the square root, but the standard deviation, sigma of x, is equal to the square root of, and then we're going to take the sum of the x squared times p of x values, and then minus the mean of x squared, right? So this is where not having to type all those values in again is going to come in handy, right? Because how this stands right now, this is the mean value, right? So in order to get this to look like we want, I'm going to need to, I'm going to store this value. So if I hit this STO button, I can store this as alpha A, which means if I type in A into my calculator, it's going to know that that's the number I want to use, right? That's the number I'm talking about. So we need to take the square root of, and then, actually, I'm not going to do the square root yet. I'm going to do second entry and then second entry again. And so what that is it gave me my entry above me storing the answer to A. Right. So then what I need to do now So I went just to the very beginning, right? So if I look at the equation, right? So right now what I have is sigma of x times p of x, right? Because that's the expected value, the mean of x. That's what's in my calculator right now. The only difference, for this part here is that my x values are squared, right? So that's what I'm going to be after now. I'm going to square each of these values, right? So to do that, I need to do second insert and then type the square button. Oops. I need to delete that 0. I did it a little too soon. All right, so now that should be right. So that should be 15 million, right? 1, 2, 3, 1, 2, 3. Yep. Right, so I got 15 million squared, and then I need to go to the next x value, which is 200,000. So I'm going to go over top that parenthesis, hit second insert, and then hit the square button, right? And then I'm going to go to the next open parenthesis, right? Hit second insert square, and then go to the next parenthesis. Right, so again, I'm doing this strategically to avoid typing in all of those probabilities again, because that took a lot. So go to the next parenthesis. Right. So then if I hit enter, what that value is the sum of the x squared times p of x, right? So then what I need to do is subtract off the mean squared, right? So remember we stored that as a, so I just need to minus the mean squared, right? And hit enter. And so now that's the value that's underneath the square root. So now I need to take the square root of that answer, and that gives me the standard deviation, right? So I'm just, strategically using my calculator to fill this out, right? So this was equal to the square root of, so this was 1,550,373.041. So that came out to be roughly $1,245. Right? So that's the standard deviation. And this value, since it's pretty large, it suggests that there's a wide range of payouts, right? Which is true, right? You can win anywhere from $0 to $3 all the way up to the grand prize, which is 15 million, right? Because standard deviation talks about the spread, right? So there's a big spread in the payouts. Right, so then part D says to the nearest million, how much should the grand prize be so that you can expect a profit? Assume no one else wins so that you don't have to share the grand prize. Right? So we don't know what the grand prize is, right? So I'm going to let little g equal the grand prize amount. So we want an expected profit of, bigger than 0. So that would be, finding your expected value and then subtracting off the $1 that you pay. We want that to be bigger than 0, right? So if we go back to this table, right, the difference here is instead of that being 15 million, this is now G units, right? So remember, the expected value of X would be equal to, we would take G times 0 point and then the 8 zeros and then 684. Right, and then we'd have plus, the 200,000 times 0 point, and then that probability, right? We would write that out here, and so forth. So rather than, rather than having to write all this out, if I think about this strategically, what I could do is multiply each of these and add those up, right, and figure out what that value would be to help me with this equation. So if I go back to my calculator, right, so I need to hit second entry a few times. There, so now I'm finally back to what I inputted in at the very beginning of this problem, calculate the expected value. I'm scrolling over left, going all the way to the beginning. And what I need to do is delete this 15 million factor, right? So I need to delete that and also its probability. Right, and then if I hit enter, what that's giving me is the value of all those others expected values, right? So in other words, if we ignore the grand prize, that would be the expected value, right? So what that does is that helps me get to my equation a little easier, right? So my expected value would be the probability of the grand prize, which is 0.00001, 2, 3, 4. So it should be 8 zeros there, and then 684 times G, right? And then we'd have plus, and then I'd have 200,000 times this probability, and then 10,000 times this probability. But rather than writing that all out, I found that in my calculator, right? That was 0.196991659, right? So this is the new expected value by just changing out the grand prize, instead of being 15 million, to be G, right? So then I need to take that expected value, subtract 1 from it, and then we want this to be bigger than 0, right? So we need to solve this equation for G, right, is what we need to do. So I can add 1 to both sides, which gives me the following: 5, 6, 7, 8, 6, 8, 4G. Right, and then next I'd want to subtract this 0.19 number. From both sides. So that gives me 0.803008,341 on the right side, and on the left I get I'm left with this 1, 2, 3, 4, 5, 6, 7, 8, 684 times G, right? I'm left with that. And then to get G by itself, I just need to divide by the coefficient, right? So I need to divide by this really small number, 0 point, and then 8 zeros. And then what that does is leaves me with G on the left side. So I'd have G greater than, and then this value comes out to be, let's see, 117,398,880.3. Right? So roughly, this is roughly $118 million. So we would need a grand prize of $118 million to have an expected profit greater than 0, right? So that's pretty large, right? So for us to expect to make something. So in the last part of this question says, does the size of the grand prize affect your chances of winning? Explain, right? So in other words, if we're thinking about this probability distribution, we're thinking about if we have various values for G, right, for the grand prize, is that going to affect my chances of winning? And the answer is going to be no, right, because the chances of winning is controlled by the probability, right? So in other words, the size of the grand prize does not affect the chance of winning, provided the probabilities remain constant. Right, so provided the probabilities don't change, changing the size of the grand prize does not increase your chances of winning, right? In fact, what it does is, why does the grand prize fluctuate? Because it's trying to get you to want to buy in, right? So maybe you're talking with your friends like, oh, did you see the Powerball's up to 250 million or something, right? So then you're like, oh my gosh, it's never been this high. Let's go buy a ticket, right? But you still have the same probability of winning. It's just the grand prize just fluctuates, right? All right, so that's all I have for this section. Let me know if you have any questions. Thanks.